Alright, section 5.6. Again, in case you haven't heard me say this in class, no section 5.5, in case you're wondering what happened to section 5.5. Probably not going to do it, you know, whatever textbook I'm going off of here, roughly. Section 5 might have been on something like the binomial theorem, if I had to guess. And we're probably not going to do that, maybe if we have time, but let's do section 6, 5.6, counting principles, permutations, and combinations. Once again, sort of changing gears a little bit, you know, like we might bust out a little bit of factorial knowledge, but it's different enough from all the sequences and series and sigma and whatever, arithmetic, geometric, you know. But anyway, so let's get going. If you recall, 7 exclamation point, that is read as 7 factorial, and it's equal to 7 times 6 times 5 times 4 times 3 times 2 times 1, which is equal to like 5040, I believe. But anyway, the counting principle usually is like, you know, when you are asked a question that starts off sort of like, how many different ways are there? How many total ways are there to blah, 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 blah? Okay, so let's just get right into some examples, shall we? Okay. Where's my mouse? All right. Example 1 says, if you don't mind me reading to you, how many different outfits are possible to make, choosing from 5 shirts, 3 pairs of pants, and 2 pairs of shoes? In general, okay, the counting principle applies specifically when you have an event, okay? Like, this is a pretty big official word in all of this lingo. If you have an event and there's m number of possibilities or choices, or the first event can happen in m number of ways, and then there's like another event or decision or something that can go another certain number of ways, and then there might be another event and another event and another event. Whenever you have like a series of events or decisions or something where each one can happen a certain number of ways, what you're going to do is multiply all those numbers together. So in this example, the first event is, well, I got to choose a shirt. That can happen 5 ways. Then I got to choose a pair of pants. That can happen 3 different ways. Then I got to choose a pair of shoes, which can happen 2 different ways. So the total number of outfits you can put together is going to be 5 times 3 times 2, which ends up just being 30 at the end of the day. But what if they need to match? Who cares? There's 5 different ways you can choose a shirt, 3 different ways you could choose a pair of pants, and 2 different ways you can pick a pair of shoes. So the total number of ways you can pick one of each, 5 times 3 times 2, which is 30. Examples that we could, that I could give to you, you know, that you could potentially see, whatever, relatable examples would be like, let's say a Mr. Potato Head example where, you know, the situation is you have so many pairs of eyes, like eye pieces you could choose to put on your Mr. Potato Head or Mrs. Potato Head. So many different hat pieces, nose pieces, mouth pieces, legs, arms, whatever, you know. And so the question would be like, how many different possible Mr. Potato Heads you could make? Or Mrs. Potato Head, or Mr. slash Mrs. Whatever. How many different potato heads could you make choosing one eye, pair of eyes, one nose, one mouth? You would multiply all those numbers together. Rolling 2 dice. That's a classic one. How many different ways are there to roll 2 dice? Like roll a die and then roll another die. And the answer here is 36 ways, because there's 6 ways the first die can land, and then there's 6 ways the second die can land, and you would multiply, right? I mean, it makes sense because you could literally do okay, you could have a 1 and a 1, 1 and a 2, 1 and that doesn't look like a 2. Was that my fault or the board's fault? You could have a 1 and a 1, a 1 and a 2, a 1 and a 3, a 1 and a 4, a 1 and a 5, a 1 and a 6. But then you could have a 2 and a 1, a 2 and a 2, a 2 and a 3, a 2 and a 4, 2 and a... Come on, work with me here, technology. A 2 and a 5, a 2 and a 6, and, 3 and a 1. I mean, you get the idea, I hope. That's going to be 36 total, 6 groups of 6. Meals, let's say you went to some weirdo buffet or something, or maybe a wedding reception, I don't know, where you could choose between 2 different entrees and then, 3 different appetizers, and you had your choice of 4 different beverages, and desserts. There was a certain number of desserts you had to pick from, and I don't know, whatever, right? Side dishes, and you had to pick one of each. You had to pick an entree, pick an appetizer, pick a beverage, pick a dessert, pick a side dish, pick your choice of silverware, I don't know. So how many different meals could you put together, choosing one of each? You would multiply them all together via the counting principle. So here's another type of situation that I would consider, a different enough situation, but definitely still applying with the counting principle. How many different license plates are possible, in the state of Pennsylvania, I guess, using 3 letters followed by 4 digits. So I know you can have vanity license plates and all this other weird stuff, but or different stuff. But only talking about the normal, I guess, license plates that are 3 letters followed by 4 digits. How many different possible license plates are out there, And this is the counting principle, because you could look at it as, okay, how many ways could the first letter happen? Or could you choose the first letter? And there's 26 ways the first letter can occur, And then you have to think about, okay, so then how many ways could the second letter happen? 26. How many ways could that third letter occur? 26. And then it's okay, then how many different choices are there for the first digit? There's 10. Don't forget about 0. Not just 1 through 9, but also including the 0. There's 10 options for each digit, each number. And so, the counting principle says, how many ways could you choose one of each and make a license plate, 26 times 26 times 26 times 10 times 10 times 10 times 10. In other words, you could totally rewrite that as 26 to the 3rd power. In fact, maybe I shall. I dropped my pen. It's okay. 26 to the 3rd power times 10 to the 4th power. Which I hope... Oh, wait. It's not the time for shenanigans. Anyway, not surprisingly, when you start to do all kinds of multiplying with this counting principle, you can get some pretty large numbers, like 175 plus million. Well over 175.5 million license plates. Just in Pennsylvania alone, and only of this type. 3 letters followed by 4 digits. Maybe one day when people stop turning in their old license plates and I don't know, whatever, maybe the population will explode enough one day where they need to add like more digits or letters or whatever, or other kinds of weird crap. Definitely an example like this whole license plate business is passwords. I mean, think about that. When you're talking about how many different passwords are possible when, like, for the first character of your password, you have all kinds of options. And then for the second character, you have all kinds of options. And then third character, all kinds of options. Letters and numbers. Maybe even, like, capital letters being different from lowercase numbers, or lowercase letters, and even throwing in special characters like asterisks and underscores and question marks and dashes and I don't even know, exclamation points, right? And passwords. This whole passwords business can, I mean, when you especially start talking about like real life, real situation, all the options for passwords, this is a different example than like the license plate thing, because when you start to think about how many passwords are possible, you'd have to like multiply. Well, let me at least start to write this out. You don't have to write this all down, but let's just say, and I'm already restricting real life here, but let's just say it was only letters and numbers. So each character, there was only 36 possibilities. You know what I mean? No capitalization matters or anything, so just the 26 letters and the 10 digits. Like let's say your password had to be like at least 6 characters long, which is pretty common. Sometimes it might be 8. I don't even remember. So let's go with 8. Let's say your password had to be 8 characters long. You'd have to do 36 times 36 times 36, yada, yada, yada. Basically, all that multiplying for the counting principle. And 36 to the 8th power, that's how many 8 character long passwords are possible in this situation, with 36 options each character. But you don't know whether someone's password is 8 characters long or 9 characters long or 12 characters long or whatever. So you'd have to do like 36 to the 8th, all that multiplying, plus 36 to the 9th, all that multiplying with the counting principle, plus, all the different 10 character long passwords, plus all the different 11. It's crazy. Passwords is, insane. But moving on to example 3, which I sort of consider a different kind of example. How many ways are there to have 5 people line up side by side for a photograph? So if you had 5 people and you wanted to line up shoulder to shoulder, side by side for a photograph, how many different arrangements, how many different ways could you have them line up? Well, think of it as the counting principle. How many options are there? How many ways are there to place that first person? How many choices do you have? 5, of course, right? But then looking at this note right here, how many ways are there for you to choose the second person next to him or her? There's just 4. And then there's just 3, and then there's just 2 options, and then there's just 1. So, like, yes, if you have 5 people, Uh, let's say Brandon, Kevin, Jason, Carl, and Allison, the youngest 5 siblings in my family. Okay, with the oldest 2 being other girls. But anyway, so you have 5 choices: Brandon or Kevin or Jason or KJ or Allison. And then let's say you place Jason, me, right here. And then it's like you really don't have 5 choices again, because as nice of a picture as it would be to pick Jason again, and then pick Jason and you can't. You don't really have another 5 choices. You only really have 4 choices, and then you only really have 3 options for that 3rd spot. So that's why this works that way. Basically, I hope you understand. And yeah, you could think of this as just 5 factorial. Well, what is this, 120 or something? Might as well write it, eh? Two, 6, 24, yeah, 120, right? Alright, so some quick rapid-fire examples. What you should probably do is pause the video, if that's not too much trouble. Pause the video, please, and try all these examples. Try them all. Try them all, and I'm going to reveal the answers, and I might do a little bit of explaining, but if there's anything you got wrong or thought wrong, then please ask me in class the next time you get a chance. But here we go. So pause the video, because I'm going to start in 5, 4, and I mean all of them, not just 1 through 3. Do all these questions all the way to, like, what is it? All the way to 8. So do all 8, okay? Because I'm going to get going here in 5, 4, 3, 2, 1. Here I go. Number 1. Now again, look, you should have read this, okay, on your own. So the bottom line is the final answer is you do 3 times 4, counting principle, to get 12. 3 ways to pick the pitcher times 4 ways to pick the catcher. 4 total ways to pick them together. Number 2. Once again, obviously the counting principle, that's what we're talking about here. First you have to pick the first letter, then you have to pick the second letter, then you have to pick the third letter, and since no letter was allowed to be repeated, you really didn't have 6 choices for all 3 letters. You only had 6, and then 5, and then 4, because no letter could have been repeated. If you were allowed to repeat, then it would have been 6 times 6 times 6, but not. Number 3, it's 2 times 3 times 2, because there was 2 ways you could have picked a bread, and then 3 options to pick the meat, and then 2 ways to pick the cheese. So picking 1 bread, 1 meat, 1 cheese, 12 total ways. Number 4, 36 total students. You got to pick a president, vice president. Now, I would hope it goes without even saying that you can't pick the same person to be all of those spots. So it's not like there really is 36 choices for all 4 spots. There's 36, then 35, then 34, then 33. And so you multiply all these numbers together, and you got to pick a president, then you got to pick a vice president. 35 ways to do that. Times 34 ways to pick the treasurer, times 33. It's a lot of options. Almost 1.5 million different ways. And that's just with 36 students. Imagine 180 or so, like we have these days. Number 5, 3 pairs of trousers, 4 shirts, 2 pairs of boots. How many different outfits if he chooses one of each? 3 times 4 times 2, baby. Number 6. This one's a little tricky, right? So I hope you thought about this very carefully and how this models or relates to the counting principle, where There's a first event, and it can happen so many ways, and then there's another event that can occur so many ways, and then there might be another event that can happen so many ways, and then maybe even another event, you know what I mean? So it's not 5 times 2. It's not 5 times 2, because that would be saying that there's 2 events. The first event, there's 5 different ways it can happen. And then there's a second event, and there's 2 different ways that can happen. That's not what's going on here. There's the first flip that can happen 2 different ways. There's the second flip that can happen 2 different ways. The next flip can happen 2 different ways. Fourth flip, 2 different outcomes. Fifth flip, 2 different outcomes. It's 2 to the 5th power. 32 total ways. Number 7, once again, this is very, very, very important in the reading, those types of things to notice. No 2 letters can be duplicated, so you can't, it's not like you have 26 options for every one of these 3 letters. 26 times 25 times 24. 3 letters you're picking. Or possibly randomly picking, I don't know. Number 8. Basically, 8 ways to start your route, 6 ways to finish. You know? It's a weird way to spell Neil. No offense. Alright, well, taking a breath here. And a little bit of cough. Because we're kind of switching it up a little bit. So, let me explain. The counting principle, again, is really about having like a certain number of events or decisions in a row where they all could happen a certain number of ways. What we are about to do can be described as like you have one group of something, whether it's people or books or whatever, right? Activities, I don't know. You have like one group of stuff, and you want to figure out how many groups, like how many groups can you make from that group, you know? Like if you have 50 people and you want to figure out like how many different groups of 7 you can make from a group of 50, that's where this combination and permutation stuff comes into play, when you're making like smaller groups from a bigger group, you know what I mean? Potentially. And what matters here is you're going to look at it as a like, okay, the 7 and 50 thing, you're going to look at it as a combination of 7 people out of 50 if the order is not important. You're going to look at it as a permutation of 7 people out of 50 people if what matters is you're putting them in a particular order. Okay, so you take, like let's say me and my 6 siblings were amongst a group of 50. You know what I mean? And, you know, just putting us together in a group of 7, that's just a combination, right? And if all you were looking to do was make a combination of 7 people, then you could only put me and my brothers and sisters together one time, you know. But if you were making permutations of 7 from a group of 50 people, then, you know, you could call a group Denise, then Emily, then KJ, then Allison, then Jason, then Kevin, then Brandon. But an entirely different group of 7 would be Brandon, then Kevin, then Jason, then Allison, then KJ, then Emily, then Denise. And then an entirely different group of people would be Jason, then KJ, then Kevin, then Brandon, then Allison, then Emily, then Denise. You know, you could keep on repeating the same group of 7, but in a different order, calling it a different permutation every time. So I hope you already can tell that, you know, there's way more permutations than combinations, kind of thing. Because in a permutation, it's all about the order of that group that makes it a unique group. So a couple examples here. How many different combinations of 3 books can be chosen from a shelf containing 8? Like, let's say you only had time on vacation or something to read 3 books, and so, like, how many different ways could you pick 3 books out of your 8 books to take with you on vacation or something? I don't think the order matters, you know what I mean? So you're just, you know, bringing 3 books, you know, with nothing here emphasizing that the order that you choose the books in is important. Like, there's absolutely no vibe at all. In fact, they're literally using the word combinations. So anyway, so we're going to be doing a combination, and here we go. For these combination questions and permutation questions, it actually boils down to a formula, baby. And here is the formula, and hey, it actually involves factorials. But as much as you probably should write this down, I have not just good news, but great news. On any calculator worth a darn, you're probably going to have this formula built into the calculator, programmed into the calculator. In fact, this formula, you can find it probably exactly where you would find the factorial exclamation point, in a probability menu, a PRB menu or whatever. And so here's what you would do. First of all, let me just kind of move this stuff out of the way. So we are essentially going to be doing like 8 choose 3, you know, 8C3, okay? C is definitely for, you know, combinations. Like, that's what it really stands for, is combinations, right? But you can think of it as, I have 8 books and I'm choosing 3. You always go NCR. In fact, that's probably what your calculator says in that menu, NCR. And but I'll get to your calculator in a second, okay? Hold on. I just want to make sure that you would write it like this, 8C3, or as a lot of teachers like myself and the great Mr. Matt Shesman and probably his son, and people like Birch and all the rest of us, you know. Who else teaches pre-calc here? Just me and Birch right now. So anyway, no other shout-outs. But anyway, 8 choose 3, okay? 8 choose 3. You know, they probably cover this in algebra too. So okay, Mrs. Clute, Miss Fetchko, you know, everyone else, I don't know. Anywho, 8 choose 3, and here's what you do on your calculator. First, you would actually have to type in the 8. Before going to your NCR formula on your calculator, you would first type in 8, then find the NCR stuff by hitting maybe like the PRB button, finding the right menu, whatever, clicking on or highlighting the NCR and hitting enter, then hitting the 3, and then enter again. And so your calculator can do all this formula stuff for you, because you can either go on your calculator, or you could do 8 factorial all over 3 factorial times 8 minus 3 factorial, you know. But this is built into your calculator, and you can just do 8 NCR3, and it's 56. So there's 56 different groups of 3 you can make from a group of 8. How about that? But an example for permutations, like in an Olympic race, how many different finishes amongst the first 3 places are possible if 7 runners are racing? 7 lanes, 7 runners, and how many different finishes, like how many different ways could you award gold, silver, and bronze in this Olympic race, you know? So think about it. Having a finish of, you know, okay, obviously I'm going gold, silver, bronze in that order. Having a finish of the American in first, Jamaican in second, sorry, Usain Bolt, and I don't know, gosh, the Australian in third. That's one finish, you know. A completely different finish would have been the Australian, then the American, then the Jamaican. Sorry, Usain Bolt. That's the same 3 runners, but since they're in a different order, it's a completely different result, a completely different permutation. Just like another completely different finish would have been, okay, the Jamaican, then the Australian, then the American. You know what I mean? So obviously order matters here. You know what I mean? And there's actually a formula for number of permutations as well. And it's this. But, well, duh. Well, I don't know. But this is also programmed into your calculator. So, and again, it's going to be NPR. So N is going to be 7, like the entire group is N. The groups we're making is R, and so so you say 7P3. And obviously the P really stands for permutations. But just like, now a little compare here, just like it sort of is almost easier to understand by saying like 8, choose 3, and use the word choose. You have 8 and you're choosing 3. 8, choose 3. Here, you know, sorry, Mr. Shesman, but and I can't even take credit for this. You know, I think of, I can't remember for sure. I think I might be able to remember one of the students that had a good idea in the past, but I don't want to be wrong. But anyway. So I can't take credit for this, but I did have a couple of students in the past, numerous students probably, come up with like really good ideas that I never knew before. So here's what I will recommend you thinking this as: 7 place 3. You have 7 and you're placing 3. Or another good idea is you have 7 and you're positioning 3, because those words pretty much, you know, the vibe with those words is that the order matters, you know. The implication of the word, you know, when you're saying 7 place 3 or 7 position 3, is that the position matters, the order matters. So again, this one you can think of as 8, choose 3 for combinations, 7, position 3, and when you throw this into your calculator, again, you would first hit the 7, then go to the NPR function, you know, in the correct menu, then hit 3, and then enter. So really, I think on your calculator, it's probably not even going to look like this. It's probably going to say 7 NPR 3, even though technically 7 is the N and 3 is the R. Kind of, whatever. It's just calculator programming. And it's going to say 210. So there's 210 different ways that you can award gold, silver, and bronze just with 7 runners. It's kind of crazy. All right. Now I'm going to hopefully go into like a whole thing that makes all this come a little full circle. And so I call this like the mutual example. So here we go. The final example on the other side of your paper, I assume, asks about the number of different ways you could potentially arrange 5 people. Right? And then we do this as 5 times 4 times 3 times 2 times 1. 5 ways to place the first person, times 4 ways to pick the second, times 3, and essentially 5 factorial. You could also think of this as a permutation question. Oh. Not only is it a counting principle question, it's also a permutation question where you could calculate, or where you would calculate, 5p5. That's right, 5p5. Because aren't you really like taking a group of 5 people and just trying to figure out how many arrangements of 5, how many groups of 5 you could make from a group of 5? But the order matters. So yeah, 5p5, which, of course, happens to be equal to 5 factorial, exactly what you would end up having if you approached it from a counting principle, perspective. Think, again, and I just said this, think of it as the number of ways to arrange 5 people out of 5 people, 5p5, So, basically, I guess before I have you try these examples, I can sort of say in general, okay? And this is where it gets a little dicey, okay? So please concentrate on what I'm saying, and I hope I explain it clearly. There is definitely a strong connection between the counting principle and permutations. Not combinations. Not combinations. Let me already give you like a sneak preview about that, okay? Let's say, okay, here we go, number one. I'll just use number 1. How many ways can a 3-person subcommittee be selected from a committee of 7 people? Oh, okay. So essentially, how many groups of 3 could I make from a group of 7? And once again, I'll just say the 7 people are me and my bros and sisters. Bros and sisters. Is that even a term? Brandon, Kevin, Jason, Allison, KJ, Emily, Denise. And so, how many different ways can we make a group of 3 from that group of 7? Does order matter here? No. So once you form a group of like me, Kevin, and Brandon, that's the only time us 3 can be together and call it a unique group, And so if you were going to do this as far as a permutation or a combination formula, it would be a combination. 7, choose 3. Which, by the way, your calculator can tell you equals 35. Because the formula is built in there. But here's what I want to elaborate, right? If by any chance you are thinking like, wait a second, isn't this like saying, okay, don't write this down. Do not write this down. I have to pick 3 people. Couldn't I think of this as 3 decisions? My first decision is I pick the first person, then I got to pick the next person, then I got to pick the next person, Isn't there 7 choices for the first person, right? 6 choices for the second person in the subcommittee, and then 5 choices for the third person. And I'm here to tell you that, if, in case you're wondering that, the answer is no. And here's why. I hope I can explain it pretty well. As my throat is starting to kill me right now. I know, like, boo, boo, boo-hoo. Crimea River, Mr. Falk. So check this out. So 7 times 6 times 5. So once again, me, Kevin, and Brandon. Jason, Kevin, and Brandon. So this is saying that, okay, I have 7 choices in the Falk family. I pick Jason. Now I have 6 options. I pick Kevin. Now I have 5 choices. I pick Brandon. Well, guess what? This mathematics, this approach, also includes the whole thing of like, okay, I have 7 choices. I pick Brandon. Now I have 6 choices. I'll pick Kevin. Now I have 5 choices. I'll pick Jason. It's the same 3 people, but in the context of this approach, they're 2 different groups, which, no, that's not what this is about. So, and then you could also think, okay, I have 7 choices. I pick Kevin. Then I pick Jason. Then I pick Brandon. You know, like, but that doesn't fit the situation, you know. So, once again, there is a strong connection between that counting principle and permutations, not combinations. So, unless you want to literally list, like, every single group of 3 by hand the long way, this is like the only way to answer this question. 7 choose 3 equals 35. Please pause the video and try all the others, not just number 2, but all the others, and see how you do. And I'm going to take it away here in about 10 seconds. I'm actually going to get a quick sip of water. All right, here we go. Number 2, which you should have read already. On here, jeez. 4 chips in a hat. Hey, speaking of the Falks, Denise randomly selects 3 chips from the hat. How many combinations of numbers are possible? They're literally using the word combinations. So that should be the only way, unless you're going to like literally list them all by hand and count them by hand. Number 3, in a horse race, how many different finishes? So this is strongly, at least you should realize that it's strongly implying that order matters. So this is like how many groups of 3 could come from a group of 12, but order matters. Bam. Number 4, okay. This is not very mysterious what they want. They're literally asking for both the number of permutations of 3 out of 4 and combinations. So hello. There it is. Calculator doing all the work for you. Mutual examples. Hey. I'm as subtle as a hammer to the head. I don't even know what I'm... Sorry, didn't... Anyway, here we go. Becky, that's not a Falk as far as I know. Becky has 9 stacks. Stacks. How many different ways can the 9 chips be stacked? Sounds to me like order matters. So 9, P9. Or you could do 9 times 8 times 7. Remember, there is a very strong connection between the permutation formula and scenario and the counting principle. Okay, so either way, but you're going to get that number. How many different playing orders are there for a game in which 3 people are playing? Once again, it could be 3p3 or 3 factorial equals 6. Now I probably should have, I'm going to go back here, pretty important. I can't believe I forgot to mention something in number 3. You also could have done number 3 like this. So maybe you should write this down. Or there's 12 different ways the first horse can happen. 11 ways the second horse can occur, the second place horse can finish. And 10 ways. So either way, you're going to get 1,320. I'm going to prove it right now on my handy dandy calculator. Just to prove to myself that I'm not crazy. Yep. So there, again, permutations and the counting principle have a very strong connection, but not combinations. Additional example. Whoa. Additional example. Hey. An urn. An urn. This always cracks me up with urns. Why would you have marbles or urns or whatever in urns? It's weird. But, hey, if you want to, pause the video and see if you can figure this out. Because I'm going to reveal the answer in 5, 4, 3, 2, 1. Hint, counting the combinations may be the best method. Because, quite frankly, this doesn't quite fit. 4 reds, 3 greens, 1 blue. 2 are randomly chosen from the urn at the same time. How many different color combinations are possible? Sometimes a situation doesn't fit these cookie cutter counting principle or these formulas. So just kind of counting. Anyway, I'm not going to emphasize this too much because not going to pop up on any quiz or test, but that'll do it for section 5-6.